So yes, on Friday I gave a talk on EMU, which is the big ASCAP Continuum Survey Project, Evolutionary Map of the Universe. And what I'm going to talk about today is ATLAS, the Australia Telescope Large Area Survey, which is a project we started a few years ago and is sort of segueing into EMU, which is why I've called it ATLAS EMU. And I'll say a little bit about EMU at the end, but this is almost entirely about ATLAS. So what I'm going to talk about today, firstly, give you an overview of what the project is and where it is, and then I'll get on to some science, and I'm going to talk, rather than talk about all these boring luminosity functions, for which my students will kill me for saying that because they're very hard to produce, but I'm going to talk about 4 little tidbits that have come out of it, rather than talking about there's too much science to cover otherwise, and then I'll talk about the EMU connection. Okay, so this is a diagram I keep on using. It basically shows where we are in the world with continuum surveys. And so this is a plot of all the major 20 centimetre sky surveys, continuum sky surveys. So you've got, oh, this isn't very bright, is it? You've got flux, 5 sigma flux limits along there, and you've got the area of sky covered up there. So at the top we've got the largest survey, NVSS, done by Jim Compton with the VLA, which covers the whole sky but isn't very sensitive. And down there you've got Fraser-Owen's Luckman Hole observation, which is the deepest radio survey yet done, which is just one point in the VLA going down to a few microtranscripts RMS. And you can see that all the other surveys that people have done basically are bounded by a line which tells you how much observing time you can get on a radio telescope. That line corresponds to a few months of observing time on either the compact ray or the VLA. And you can see that ATLAS, right now I've cunningly placed the line so ATLAS is just going over it, which is either due to the generosity of the Time Allocation Committee or due to our ingenuity. And I'd like to think the latter, but I suspect the former. So here we are in ATLAS. We're pushing out into this great uncharted phase space where all these observations are waiting to be made. And of course, once we get ASCAP going and Meerkat, there's all these other fantastic surveys like EMU and MIGHTY, which sample that phase space. But I'm going to talk about ATLAS right now. So I'll just go back a second. In fact, so just to show you where we are, that it's a bar. That's where we started with data release 1. And over on the left is where we hope to be at the end of this year with data release 3. And that corresponds to an RMS of 10 microtranscript sensitivity, which is actually the same as EMU. So the left-hand side of ATLAS and EMU line up. But ATLAS covers 7 square degrees, whereas EMU covers the whole sky. When you're down to 10 microtranscripts RMS, surveying continuum sources, that takes you out to quite high redshifts. So for star-forming and starburst galaxies, we have a median redshift of about 1.1 in ATLAS. These numbers aren't measured. These are from the SCAD simulations, the SKA design study simulations, which are essentially an encapsulation of everything we know about the radio sky. But based on that, our star-forming galaxies should have a median redshift of about 1.1, and our AGN have a median redshift of 1.9. But you can see what happens is that the star-forming galaxies, that these ones here, are mainly low redshift with a tail that dribbles off like that. AGNs go right off, and they never actually go to 0. With AGNs, we can actually go to the edge of the universe. You get a radio-loud AGN, put it any redshift you like, we can see it. Assuming the universe, nothing starts before about z equals 10 or something, we could see a radio loud AGN at z equals 10 without any trouble at all, if indeed such things existed. But with the model, we expect a median redshift of about 1.9. So to put that in context, because redshifts are deceptive things, if you think in terms of time since the Big Bang, to give you an example, probably many people here are familiar with the 2D FGRS, which is spectroscopic optical redshift survey. And that goes back about that far towards the Big Bang. So we're up here, Big Bang's there, that's how far 2D FGRS goes, and by comparison, ATLAS goes all the way back there, provided we're talking about radio-loud AGNs. If we're talking about star-forming galaxies, we probably do about the same as 2D FGRS. Okay, so the survey goal is to image 7 square degrees to an RMS of 10 microtranscripts. And this is, we expect to at the moment, we've got about 2,000 galaxies we've discovered, and at the end of the project, will be about 10,000, which is enough to start encountering rare objects, rare and faint objects, which you wouldn't have seen before in radio surveys. This is what I mean about going into a new area of phase space. And the things that are driving it are questions like, when did the first massive black holes turn on? If you start with conventional models, how do you build a 10 to the 9 solar mass black hole? You have to bang other black holes together through galaxy mergers and things. And the trouble is that process takes billions of years, whereas we know some of these things are way back in the first billion years after the Big Bang. So we know our models are wrong. We'd really like to pin this down. What's the relationship between AGNs and star formation? So we know that AGNs, black holes, somehow affect the star formation. You see the two changing in luminosity together. We don't know why. So lots of questions like that. I could actually show you the grand panoply of what's driving ATLAS, but it'd probably bore you stiff. But this is the inside of my brain, which is a scary place. And way back when we designed ATLAS, I sort of wrote down these science goals and then tried to translate them into actual observable things, and then tried to group them into PhD projects and things, and that's what we ended up with. And a sort of map of who's doing what. I don't expect you to read that, but it's just a scary place. That's why I'm not going to tell you about everything that we've done in ATLAS. It's too messy. What I am going to tell you about, we've got 5 PhD students at the moment. So Minnie Mao, she's just finishing her PhD. She's got a postdoc at NREO. And her job was to trace the evolution of AGNs and star formation by doing spectroscopy on our radio sources, and in fact she also looked at large-scale structure. Chris Hales, who's also about to finish and has got a Jansky Fellowship at NREO, he's been looking at the polarization, and his goal is to see if we can see the cosmic magnetic fields and determine the origin of magnetism. Well, we're not going to actually measure the intergalactic magnetic field, but we're going to put a really good limit on it. Kate Randall, who's actually submitted, has been using spectral indices to understand CSS GPS sources. For those of you who aren't familiar, CSS, that means compact steep spectrum. That's a source with a nice steep radio spectrum, but which is less than a few kiloparsecs across. And GPS sources are sources whose spectrum does this and peaks at a few gigahertz, and these are very early AGN. So those 3 are just in the process of finishing. And then we've got Peter Zinn, who's about halfway through his PhD, and he's using polarization and spectral indices, again, to look at evolution of AGN. And Jordan Collier, who's just started, who's looking at the earliest stages of AGN using the CSS GPS sources and also IFRSs, which I'll tell you about in a minute. And there's a whole load of holes which aren't there. So if anybody here wants to do a PhD project, we've got lots to do and really good data to do it with. The nice thing, if you joined ATLAS now, we've actually done all the hard work. We've actually got all the data. And it's just a question of mining it for science and checking out all the papers, which we're starting to do now. There's it's Team ATLAS a couple of years ago. The name's down on the left, and we tend to be a fairly sociable group. And 3 people who couldn't make it have parachuted in courtesy of Photoshop. And then so that's if you like the core group. We meet every week by telecom, and there's an extended team who we consult, whose brains we tap into for particular things. Okay. So I've talked all about the radio data that we're getting, but it's not just a radio survey. It'd be completely useless, actually, if it was just a radio survey. We chose this 7 square degrees initially to be coincident with the SWIRE survey, which is a survey being done by Spitzer, was being done by Spitzer, it's finished now. And so there's these 2 big fields, one centered on the Chandra Deep Field South, the other centered on the Elias field, and we basically chose those. And they seem to have become the fields of choice for many other groups. We also now have optical photometry, Mini and others doing spectroscopy on all the sources. The goods field is right in the middle. The Chandra Deep Field South, we also include the deepest X-ray observations. The new Vista telescope is targeting these 2 areas with video. serves as the largest space telescope in terms of time, largest amount of time ever allocated on space telescope with using the warm Spitzer, and again looking at these two fields to get really deep in the mid-infrared. The Herschel Hermes project is targeting that, the primers, and so on and so on. I could go on for ages. And then there's also GMRT and other observations. In the radio, as well as just measuring the continuum, we're doing polarization, spectral index, and VLBI on the entire field, which this is run by Enno Middelberg, using wide field VLBI techniques. So our current status, I think we're about 1 year away from the end of finishing all the data analysis. The science papers will continue coming out for quite a while after that. We've finished all the observations. Right now we have an RMS, remember our goal is 10 microjunskas. We have about an RMS of about 20 to 30 microjunskas. The first data were actually released way back in 2006 and 2008, and that's where the data stood then. And we're at the moment, we're down to 15, so that's what's been published when I say that. We are actually down to 15 microjunskas, and in Stokes V, we actually do get down to 10. So in principle, we can get down to 10 microjunskas across these fields, but whether we actually get there, that's work in progress. What it actually looks like, so this is the radio superimposed on an infrared field, and it's a whole mixture. There's a star-forming galaxy, that's obviously an FR2, AGN with a black hole in the middle and two radio lobes either side. You see the problems of cross-identifying with infrared is that things like this are really easy, where the radio is bang on top of the infrared, and that's sort of easy because you've got absolutely nothing there, and you've got an infrared source in the middle, but other cases can be really quite difficult. And so that's another area. And you can see we're going to have exactly the same problem with EMU when we start doing the whole sky with ASCAP. And so we're using ATLAS as a test bed to develop techniques that we'll then use for EMU. Right, this is a better look of what the field looks like. It's a typical bit of the field, typical in the usual astronomical sense. It's the most interesting bit of the field. And if we blow up part of that, you can see a nice wide-angle tail there, and a nice radio relic, and a nice FR1 there. From that wide-angle tail, we know there's a cluster there. You only get this is a radio galaxy where the jet's been blown back by the intra-cluster medium, and so that tells us there's a cluster there. And it's interesting. We see about one of these every square degree, so we've got about 8 in our 7 square degrees, which means that with EMU covering the whole sky, we'll get about 30,000 clusters detected like this, compared to of order 10,000 clusters known in total at the moment. So that's what the data looks like. Actually, that's the old data. The new data goes even deeper than that. In spectroscopy, our highest redshift so far is 3.2. A little bit disappointing. We are pretty certain there are Z equals 6 objects in there, but they're buggers to measure redshift for. And we know they're in there. That from the statistics, they have to be there. But getting enough telescope time to measure redshifts is very hard. So we're looking at an object here which is just 2 billion years after the Big Bang. Our highest redshift strong radio galaxy is 2.98 there. Okay, so the data products, this is all getting a bit boring, isn't it? I'll move on to some science in a minute. So data release 1, way back in 2006 to 2008, which I've just talked about. Chris Hales is working hard about to release data release 2, which is largely the same data, but analysed more carefully and also with a focus on polarisation. And it's also got a bit of extra data, so it'll go a little bit deeper. But data release 2 will be available, it's on my laptop now, but hopefully it'll be published in the next month or so. The thing that's really occupying us at the moment is data release 3, which is the final ATLAS data release. That's the one which I would say we're trying to get it down to 10 microjunskas. And this includes a whole load of observing after the CAB upgrades to the Australia telescope. Oh, this is an old slide. Likely to be a challenge. Yes, it was a challenge, but we overcame it. Okay, and so there's a whole load of other stuff. I won't bother going through this. There's a whole load of papers submitted or in preparation. It's great on a large project like this. You spend 4 years slogging your guts out up to your elbows in data, and at some point all the science comes out, and that's just where we are right now, which is quite nice. Okay, to give you an example of the sorts of things that are coming out of it, this is actually Minnie's main thesis project. So this is the luminosity function for star-forming galaxies. Okay, so there's luminosity up there. That's how many sources per cubic megaparsec you have of a particular luminosity. And as you can see, low luminosity galaxies are more common than high luminosity galaxies, so no surprises there. Then if we plot the different lines as a function of redshift, what you see, I don't know whether you can make out the symbols, I can tell you what it's saying is that at higher redshifts, there are more high luminosity star-forming galaxies. This is the familiar thing of downsizing that we all know about. So this isn't a surprise, nice confirmation that A, we've confirmed the result, B, we've probably done everything right. We're saying that the universe was a more active place at Z of 0.5 than it is now, more star-forming going on. Nothing really very surprising there, just a sanity check. If we look high luminosity AGN, again, so the lines here, this is from Mausch and Sadler. It's one of the, if you like, the standard results. At high redshift, Sadler show that high luminosity galaxies are somewhat above their low redshift line. Again, there's some luminosity evolution of high luminosity AGNs, and we sort of, our orange line sort of joins on with those, and at low luminosity joins on with their low redshift line. Again, no surprises there. This is where it starts getting interesting. So these are the low luminosity AGN. Sorry to get into details, but remember, Atlas is going a lot deeper than other radio surveys. So whereas people have only been seeing high luminosity AGNs at reasonable redshifts, we're going right down and looking at these things with a piddling little black hole in the middle of a galaxy, and we're asking the question, what's the luminosity of these things look like? Here's the Mausch and Sadler line, and you can see we're way above it. And interestingly, Paolo Padovani also made a measurement similar, and his agrees exactly with ours. And the interesting thing is that everybody criticised Padovani's result. They said he must have screwed up, because as far as we know, there's lots of other evidence suggests that low luminosity AGN do not evolve like this, and yet the fantastic agreement between his result and our result says, no, this isn't just that Paolo's, either we've both screwed up in exactly the same way, or there's a real effect. And I have to say, we really don't understand it. I'd love to say it's because low luminosity AGN are evolving after all, or the local population is different from the high redshift population, but none of this actually quite works. So this is a puzzle. We've submitted the paper and we've gone through the possible reasons and said, well, we don't actually know. We don't understand what's going on here. When we get to our later data releases, we'll get these error bars down. Maybe we'll get more light onto it then. It could be cosmic variance or something like that, but again, the numbers don't really work. Okay, so that's where we are with the sort of broad goals of the project. Now I'm going to tell you about 4 surprises that we've had, which is probably sort of more interesting in some ways. Okay, if you look in the local universe, it's a well-known fact. I was taught as an undergraduate that high-powered radio galaxies are always associated with ellipticals. You never get a spiral with a high-powered radio galaxies, right? That's what we are all taught. It turns out there are a couple of local exceptions. That's NGC 612, and everybody's, wow, it's a really weird object. It seems to have a spiralish galaxy, and yes, it's an FR1, and there's another one. But at high redshift, it doesn't seem to happen. So we do know that at high redshift, there's been evidence for a while that you get star formation apparently lined up with radio jets. So AGN activity seems to be triggering star formation only at high redshift. You never see this in the local universe. So there's a big difference between what happens in the early universe and what's happening now. In Atlas, we found 50 objects which appear to be star-forming galaxies. That thing there's got a lovely spiral SED, and it's got a bloody great FR2 coming out of it. You never see that almost never see that in the local universe. And we've got about 50 of these objects. And they're very weird. So Mini invented this awful acronym PRONGS, which I don't think is going to catch on. So they're rare in the local universe. We're finding they're common at high Z. It's a lot of these probably have ULERGs, ultroluminescent red galaxies, with an AGN in the middle. This is actually consistent with some of the models of how you make black holes. So you take two gas-rich galaxies, each of which has got a moderately sized black hole in the middle. You smash them into each other, cause a whole load of star formation, whole load of dust. You see it as a ULERG. In the middle, the black holes are, stuff is accreting onto them, lots of luminosity there. And eventually the luminosity from this AGN in the middle would probably quench the star formation, and it will turn into a high luminosity standard radio galaxy. And it could be these things are this process going on, and we don't have this process going on in the local universe. So it also makes sense. Here's an extreme example. It's actually outside the Atlas field, but it's rather nice. So it's a ULERG. In the optical and radio, you've got this featureless blob. And its spectrum and its SED and everything about it shouts star formation. But it's a strong radio source. It lies above the radio infrared correlation. And when we look in the radio, it's a bit faint, I don't know whether you can see that, there is actually a double-lobed radio source. You'd say that was an FR2, except that the size is only 1 kiloparsec across. And that's buried right deep down in the middle there. And the amazing thing is, the power of this, it makes it a really high luminosity radio galaxy. There's absolutely no clue to this in the optical or the infrared, because it's just buried under so many magnitudes of extinction in this thing. So this is one that we're studying in detail. We've also detected CO from it. We're going to look at it with ALMA. But we suspect these actually might be fair. This is a fairly low redshift, 0.327, but we suspect at high redshift these things are fairly common. So that's a surprise, all these AGNs which are not associated with ellipticals. What it's telling us is, in the past, people used to classify galaxies, and this is a completely appropriate thing to do in the low redshift universe, using line ratios or whatever. And people say, yeah, star formation AGN, star formation AGN. And what this is telling us is that at high redshift, composite galaxies are almost the norm. A typical galaxy will have an AGN and a whole load of star formation going on. And you can't really classify them as star forming or AGN. You've got to talk about what fraction of the luminosity is being generated by the AGN and so on. And then we want to look at how this ratio changes over time and with merger history, which is Jordan's PhD project. Okay, our second surprise. When we started the project, the Spitzer guys told us that Spitzer is so good at detecting these galaxies that anything we find in the radio will be detected by Spitzer. And so I was a bit perturbed to find about 50 sources like this, where we've got a lovely radio source and absolutely nothing whatsoever there in the Spitzer image. And initially, of course, I assumed that something wrong with the data, or maybe there's artifacts or side lobes. After a lot of work, we now know they are very real, and there is this class of object we've found, which we call infrared faint radio sources. With hindsight, if I'd known these were going to be important, I would have thought of a really sexy name. At the time, it's just a little glitch in the data. Infrared faint radio sources, you know. And as you see, there's a whole load of papers being written on these things now. Yeah, should have faintars or something, I don't know. Good acronym involving an Australian marsupial, preferably, but anyway. So there's two examples of these things. They're really very strong, 6 millijanskis, and nothing there at all in the infrared. We don't see these in the local universe at all. And so we think, our first idea was these could be high redshift AGN. Maybe these are the Z equals 6 AGNs that we were hoping to find. So we spent using that SERVS survey, which I talked about, with 1,400 hours on Spitzer. We actually stacked the 3.6 micron data on these things, and we get this sort of detection. It's a 1.5 sigma detection, which nobody would believe. So we call it an upper limit, actually. And that's a median of 39 IFRSs. So they're suddenly very, very faint. and this puts quite strong constraints. So the point is, if you take something like an ordinary radio-loud galaxy, and you can ask the question, how much extinction do I have to put in front of it, or what redshift do I have to put it before I stop seeing it in this image? And the answer is a lot in both cases. We've looked at a number of them with VLBI, and a third of them so far have got VLBI cores. Like that, so they're certainly real. That rules out being things like radio lobes. This particular one is reasonably steep spectrum. If we look at the spectral indices, oh, this is an awful picture. Okay, so the light things there are the IFRSs. This is where most radio galaxies and things sit. That's 0, -1, -2, -3, -4. So you can see that some of the IFRSs go up to -3. They're very steep. And in fact, this is old data, I think. In fact, none of them are less steep than -1. So they are steep spectrum objects, and as you may know, high redshift things tend to be steep spectrum on the whole, for reasons which still aren't clear. So if we make a plot, so the critical thing about this is the ratio of radio to infrared. That's the odd thing. And so here, this is a plot of various types of objects with that ratio, and the IFRSs are up here. This is the range of objects we see up here. So sub-millimeter galaxies, starbursts, radio quiet quasars down there. The thing that gets close are radio-loud quasars, approach, but not quite up there. 3C273 almost gets up there. These dots here are high redshift radio galaxies. These are the very high redshift things that Carlos de Broek and people find. And clearly that matches really quite well. So this is supporting evidence that these things probably are high redshift radio galaxies. So if we now take those high redshift radio galaxies and make a plot of redshift against 3.6 micron flux, you can see there's a rough correlation like this. This is very similar. There's a very well-known KZ relation with K-band infrared flux, which does a very similar thing. And on this scale, remember I had a limit of 0.2 microjanskis for the 3.6 micron flux, which is about down here somewhere. So you would say, if you just put it on that line, that has to be about Z equals 7. Now, I'm not actually claiming these are Z equals 7 because it's a very rough correlation. There's all sorts of possible systematic effects. But again, it's supporting evidence these things probably are high redshift. So what are they? Not consistent with an L-star galaxy at low redshift. This is just going to the individual sources. You can explain some of them by obscuration and so on, but the majority of them show that they probably are high redshift, dusty radio loud AGN. We've been trying to get spectroscopy on these things with the VLT, and it's very hard given that you can't actually see them in the continuum. But a couple of the brighter ones have shown up a spectral line, and they seem to be about Z of 3. Those are the brightest ones. And so my guess is the fainter ones are higher redshift than that. But actually measuring this is really hard. It's really hard trying to study something you can't actually see. Okay, third surprise, radio far infrared correlation. I guess everybody's probably familiar. If you take star-forming galaxies and you plot the infrared luminosity against the radio luminosity, you get a beautiful correlation over many orders of magnitude. It works really well for star-forming galaxies, and AGNs depart from that. If we take these are some of the Atlas sources, 70 microns, you can see the star-forming galaxies going up there, following the correlation, and these things up here are AGNs. So it's actually quite a good test for seeing if you've got an AGN in a galaxy, as if it departs from that correlation. Okay, there you are. Star-forming galaxies and AGN. All right, so all this we understand. That's all fine. If we look at going to 24 microns, so it's a little bit more complicated, but that's where we've got most sensitivity with Spitzer, and we plot all the Atlas galaxies there. And again, you can just about see you've got the star-forming galaxies going up there, and you've got the AGNs going up there, and you can see it's essentially two separate populations which get merged and hopelessly muddled down there. Right, okay, all that's no surprises there. Now, can we, what I was hoping was going to happen as this picture came on, can we actually push down below there by stacking? I assume everybody's familiar with stacking, right? You get lots of images of something, of a particular type of object, you add them all up, and you take the mean or median of all those objects, and so that enables you to go way below the detection limits. So we did this with the Atlas Galaxies, and you can get, this is, at the time we had 30 microjansky RMS, and we were able to get down to very low fluxes, down to a microjansky or so with this. You can see, so these are stacked images. Each of those typically got a few hundred objects in, and you see there's a very good detection in the middle of each of those. And so we can now make a plot of the radio far-infrared correlation at very low fluxes, and they come down here, which is very nice. So the correlation extends way down there, way down below where we're seeing, which is interesting. The correlation still works. That puts some good, we don't actually know the mechanism driving this, and this puts some good constraints on it. Slight problem is that it misses the main correlation that we see. And we worried about this for months, trying to find out, we must have made a mistake. And in the end, Brian, who's leading this project, said, publish and be damned. So we did publish and we were damned. And everybody said we'd obviously made a mistake. And you can say in the papers, all the things you've tried, as much as you like, but obviously you've screwed up some way in your stacking, obviously. Anyway, it turned out we hadn't. That more recently, we found it depends on the way you select them. This applies to other people as well. And it's a caveat for stacking. It depends where this line occurs, depends on how you stack. If you take radio selected objects, you have that line. If you take infrared selected objects, you have that line. Because if you infrared selected, you pick up objects over here, which are infrared luminous, but maybe below your radio sensitivity limit, which is what we're doing here. So the answer is actually biased by the way you select your sources, and it's a real cautionary tale for stacking. I think a few years ago when stacking first started to be popular, everybody's stacking everything in sight, and I think we're starting to learn to be a little bit more careful. There's a lot of very subtle effects come into play when you're stacking. Okay, so I call this surprise 3A. I'll show you 3B in a second. The infrared excess sources, which we saw on the right, which nobody even knew they existed, we think they're radio quiet AGN, and just got a paper on this in preparation. Anyway, I'll actually skip over this. More work needed, definitely. Okay, surprise 3B. How does FRC vary with Redshift? To do this, we measured that correlation. In this case, we used 70 microns, which is more reliable, and plotted that as a function of Redshift. It sounds so easy. It's incredibly hard to get rid of all the selection effects. And essentially, these lines are the models. So you wouldn't expect it to be level, because you've got things like radio sources have got a spectral index minus 0.7 or whatever. And so at high redshifts, you have to make K corrections, which change this. So this is just making reasonable sort of K corrections, these lines. And our data points, and we tried processing the data in various ways, and they basically fit the models. This is actually surprising. It's saying that the radio far-infrared correlation works right up to redshift of 3. But that's not what we expected. There's a thing called inverse Compton cooling, where the cosmic microwave background interacts with electrons and robs them of their energy. Basically, the electrons accelerate the microwave background photons to higher energy. And because the universe is expanding, the density of the cosmic microwave background increases as 1 plus z to the 4. It's a very strong function of redshift. And so we expect the cooling of electrons to go as 1 plus z to the 4. And so we expected that above z of 1, this radio far-infrared correlation should go blur as the electrons lose their energy. And it's not, it's constant. So it's saying that either the physics is wrong, inverse Compton cooling doesn't work, we don't think it's that, or else somehow it's not cooling the electrons in galaxies, or something. Our best guess is that, in fact, what we're seeing is the tip of the iceberg, that you've got some enormous buffering going on, where there's energy going in and out of these galaxies, and a sort of thermostat mechanism which is maintaining the energy of the electrons. But it's new. I mean, it's, you've got to. So there's room for some theoreticians start working on this. Right now, we don't have a good model other than some hand-waving plausibility arguments. So that was a real surprise. Right, surprise number 4. Going back to stacking. We thought it'd be a good idea to find out the flux of a radio-quiet quasar. That can't be too hard. You get a sample of optically selected quasars. You throw out all the ones where you detect the radio. You just get the radio-quiet ones and you stack them up, and that will tell you the flux of a radio-quiet quasar, which isn't known. And there's 2 hypotheses out there at the time. One said that radio-quiet and radio-loud quasars are 2 completely different objects, in which case presumably the luminosity function is going to have a bipolar distribution. Or else it's just that there's this broad distribution and the radio-quiet quasars at the tail end. So we should be able to test this by stacking and looking at the luminosity distribution of these faint sources. So we took 300 undetected radio-quiet quasars. We actually used VLA data rather than Atlas data for this because they go a bit deeper. And we had a good undergraduate working with me at the time last year. And there's the answer, very quickly. After about a week, we had the answer. The flux of a radio-quiet quasar is 2.62 microjanskas. Good. It doesn't actually tell us very much that we wanted to know. We've got a number, that's it. It doesn't tell us anything about the physics. What we really wanted to know was what's the luminosity function. So, okay, you divide it into bins, you get some luminosity function, and you realise that's also not telling you anything, because it could be that in each bin, all you're doing is taking a few sources which are brightest at the top end of the bin, adding it with a whole load of other things, and it's not clear what the luminosity function is actually telling you. So we started playing around, and we talking to various people like Jasper Wall. Said, why don't you try this, why don't you try that? We tried a technique called jackknifing, where you take subsamples of the data. So we've got 300 quasars. Suppose we take 100 at a time, and we do a stack in that 100. Then we take another 100 randomly, do a stack in that one, take another 100 randomly, and so on. So we've got all these stacked fluxes from subsets of the data, and then we arrange them, just sort them in order of increasing stacked flux. And we get a curve like this. Now, supposing all the sources were exactly the same luminosity, or same flux rather, then it wouldn't matter how you selected the sample, and you'd get a horizontal line there. So you had a horizontal line, it said there's a uniform population. Okay, supposing you had a few really bright sources, and everything else was 0. In that case, you'd have a spike here, and then something flat down there. So the shape of this curve is actually telling you about the flux distribution of your stacked sources, way below your flux limit. And this is really interesting. We realise we've stumbled on a new technique for not just stacking data, but understanding the flux distribution of sources below the limit. And so that's pretty well where we've got to. There's a few examples of the sort of thing I was talking about. That's our data there. If you take the SCAD simulation with no noise, unfortunately, that's why you've got steps in it, you get a curve like that, which is quite different. So it's saying our data is inconsistent with SCAD's, which is good. If it's Gaussian noise, you get a shape like that, and so on. And clearly what we need to do is to develop a technique where, well, what it's actually saying is the shape of this curve here, you can imagine writing a transform which turns that into a flux distribution, where you've got redshifts, turn it into luminosity distribution. You can imagine just writing down an equation which does that. I've no idea what that equation would be. So instead of that, since we're not clever enough to do that, we can do it the other way around. We say, well, let's look at the models we're trying to test. Let's run a Monte Carlo simulation using our assumed luminosity function and redshift distribution and so on, and see if we can reproduce this. And so that's what Glenn spent many months doing, and we found we couldn't actually reproduce this. We haven't hit on the right model. The obvious ones don't work. As you can see, SCADS doesn't work. So this is actually really going to be a powerful technique, but what we do have to do is to work on the technique a bit longer and develop some algorithms for doing this. Okay, so I've shown you some of the highlights of Atlas. There's lots more I haven't had a chance to talk about, but I'm here all day, so feel free to chat to me about stuff. The role of ATLAS is changing. So I've talked all about the science in ATLAS, but of course we've got EMU on the horizon now, as ASCAP approaches, at least 12 antenna configuration approaches completion. We're actually using ATLAS right now as a training set for EMU you're asking about statistical redshifts. So we're developing this statistical redshifts technique as well, using ATLAS as a test bed. And then we also, because we're doing polarization, we're also thinking about the POSSUM project for ASCAP and what we need to be doing for that. So I showed you this earlier. This is where EMU lives right out there with the same flux as ATLAS. So we actually know that what the sky is going to look like for EMU. It's just there'll be a lot more of it. And so we can actually use ATLAS as a really good test bed. EMU itself, I'll just give you a quick rundown if you're not familiar with it. So we're going to map 75% of the sky. It'll go 40 times deeper than NVSS, also 5 times better resolution than NVSS, and it will also have better sensitivity to extended structures because the shortest ASCAP baselines. So we expect to get about 70 million galaxies out of EMU, and all the things we've been doing on ATLAS we'll then be doing with a database of 70 million galaxies. We won't be looking at them by eye to do the cross IDs, I can tell you that. And so we're also developing a whole load of software for doing things like automated cross IDs. I think I won't, well, okay, we'll go through very quickly. So the things that are driving EMU are in most cases similar to those of ATLAS. Looking at the evolution of star formation, trying to understand how not just the universe was a much hotter, busier place 5 billion years ago, but also which galaxies were doing that. Was it the ones with the AGNs? Was it the ULERGs? Similarly, what's happened about the massive black holes? How do binary black holes work? How do we form the black holes so early? And why is it related to star formation? Something we can't do with ATLAS is do any cosmology. EMU is large enough. It turns out we can do some fantastic cosmology, which I'm going to tell you about in a second. And of course with EMU there's things like just finding those new objects which are out there, and other bits and pieces. And to give you one taste of what we can do with EMU, we just stumbled, this isn't even in the EMU proposal. What happened, I noticed this paper by Racanelli using NVSS and the integrated Sachs-Wolf effect to constrain dark energy, and he got a 4 sigma detection, and it's shot noise limited, so I reckon we should be able to do a square root of 40 better. So it's a 20 sigma detection, and based on that sophisticated calculation, I started going around theoreticians, and the Portsmouth group got basically spun up about it, and it turned out there's even more than I'd realised. So yes, we can do tests of dark energy. It's not just integrated Sachs-Wolf effect, there's a couple of other effects we can use. But the bottom line is we can do things like, this is an example of modified gravity, testing the parameters of general relativity. It could be that general relativity is wrong, and that's causing dark energy. Standard general relativity on this parameterized version is that cross there, with eta being 1 and mu being 1. And our current error ellipse from all our measurements is that large one there. Best value is over there, that's sort of arbitrary, but just suppose that was right. The error ellipse from EMU is that tiny ellipse there. That shows how well we do with EMU. This is just using brute force statistics on EMU data, looking at things like integrated Sachs-Wolf effect, clustering, and cosmic magnification. And so it's also going to be a very powerful cosmology machine. I'm going to finish there. Thank you.